Hi, this is Presh Talwalkar. In this video, I'm going to illustrate an amazing fact from geometry known as Pascal's Theorem, or the hexagrammum mysticum. We'll get right to the examples. We'll start out by drawing two different lines, and on each line, we'll pick 3 points, A, B, C, and on the other line, A prime, B prime, and C prime. We're going to connect some of these points together to get our result. So we'll start out by connecting A with B prime and correspondingly B with A prime. You'll notice that these two lines have a point of intersection, and we'll mark that with a green dot. We're going to draw 2 more pairs of lines, so we'll draw AC prime and correspondingly CA prime. And you'll notice that these 2 lines also have a point of intersection. We'll mark that with the green dot. Finally, we'll draw BC prime and CB prime. And once again, these 2 lines have a point of intersection, which we'll mark with the green dot. So here's the result. Here's Pascal's theorem. It's that these 3 points, these 3 green dots, will always lie on a line. They will always be on the same line. And to illustrate this, it will even be true even if I try and squish this figure up. You'll see that these 3 points are always on a line. And I'll try and deform it again. These 3 points remain on a line. And we'll return back. These 3 points are always on the same line. And this will be true no matter where you pick the points for the 2 different lines. The story gets even more interesting that we can do this with other shapes. So we'll start out with the circle, and we'll pick 6 different points, and we'll connect exactly the same pairs of lines that we did before. So we end up with a set of 3 points, and you'll very easily see that these are on the same line. And while I started out with the circle, this will be true even if we have an ellipse. And no matter what the shape of the ellipse is, these 3 points will always be on a line. Let's get more daring. Let's start out that we'll have an ellipse, but this time we're not going to put A, B, C all next to each other. We'll mix it up. So now when we connect the lines, it looks like we don't have any intersections. We just have a hexagon, which is inside of an ellipse. So what we need to do is we actually need to extend our lines beyond the shape. So we'll extend AB prime and BA prime until they do intersect at a point. And we'll continue so that we keep extending the opposite pairs of lines until they intersect. And now we have 3 points, which we've denoted with green dots. And lo and behold, these actually are on the same line. And this again will be true pretty much however you draw the shape. And we'll try and deform it. You'll see that this is always, these 3 points are always on the same line. Let's get a little creative. We'll take a parabola, we'll draw 6 different points, and we'll connect the same lines that we've been connecting. Once again, we found that the 3 points of intersection are going to be on the same line. If you really want to be daring, our final example will be with the hyperbola. We'll pick 6 different points and connect the relevant pairs of lines. And almost like magic, these 3 green dots are on the same line. The reason this happens, it's known as Pascal's theorem, which is from any 6 points on a conic section, when you draw out the lines AB prime, B prime A, AC prime, C prime A, and BC prime, C prime B, as long as those, none of those pairs of lines are parallel, as long as they're non-parallel pairs of lines, the points of intersections of those lines, those 3 points, will be collinear. And so that's why it always worked when we had a hyperbola, parabola, ellipse, or a circle. And to go back to the first example, we started out with 2 pairs of lines. The reason that works is Pascals theorem. I provided some links in the description, which will get you to more details of the math and proof of why it works. I hope you enjoyed this video. Please subscribe to my channel. You can catch me on my blog, Bind Your Decisions, on Twitter @PreshTalwalker, or get my ebooks at Amazon.